Hey everybody, welcome back to Chem 104 lecture. We are starting chapter 7. For this chapter, there are actually 3 short videos. The reason I did this is because it's kind of like 3 mini chapters. The chapter 7 in your textbook, it kind of covers 3 topics that are spread out over more like 2 or 3 chapters in like a traditional chemistry textbook. This is more of a brief skimming of each of these topics. So I wanted to put it in more bite-sized pieces so you can kind of watch, get what you need to get, and if you need to revisit something, it's a little bit easier for you to revisit. You'll understand why I say that when we get to parts 2 and 3. So part 1 should be pretty easy peasy. We're just talking about the types of chemical reactions, evidence of chemical reactions, things of that nature. No math. But there will be math in chapter 7. So, make sure that you watch all 3 parts, not just 2, 3. So like I said, in this chapter, we're covering chemical reactions and quantities. We'll start with the chemical reactions part first, and then in parts 2 and 3, we'll get more to the quantitative stuff. First section, we're looking at the equations for chemical reactions. We'll remind you of a chemical change. Remember that a chemical change occurs when a substance is converted into one or more new substances. Those new substances have to have a different chemical formula and different properties. We're going to work on balancing equations, and we're also going to identify the number of atoms in the reactants and the products. So again, chemical change, which is what this chapter is about. Chemical change means a chemical reaction. There are lots of different ways that you can observe a chemical reaction. The ones that we're going to cover are the formation of bubbles, change in color, production of a solid, or a change in energy. So changing color. The example here is when iron rusts. Rust forms when you have a metal interacting with oxygen. Okay, that iron, if you ever lived in a northern climate in the US, like Michigan, then you will see some rusted out cars. That is because oxygen does a doozy on the body of that car. That is a chemical reaction. It's also a change in color because you can see how you have that shiny metallic luster on those new nails. Then the old ones are kind of brownish red. Change in color, that means chemistry has happened. Another type of evidence, which I should mention, you don't have to see all of these pieces of evidence to suggest a chemical change has occurred. You really only need to see one. So you might see a change in color, you might see formation of a gas, but you may not see both of them. So if you mix 2 things together, 2 aqueous solutions, and all of a sudden you see gas forming, those bubbles, that shows you that something's going on there. Or if you take a piece of metal, an active metal like sodium, and put it in water, there's going to be a lot of bubbling going on. You're forming hydrogen gas. So formation of a gas, where you see lots of bubbling and fizzing, or it could be a little bit of bubbling, that's a chemical reaction. We've also got the formation of a solid, which is called a precipitate. When you take 2 aqueous solutions, combine them, and then you have a solid form. Here, we've got potassium iodide and lead nitrate added together, and then you see a yellow solid form. That yellow solid is actually lead to iodide. And the last one, we've got heat being produced or absorbed. That's like a change in energy, right? So we can talk about endothermic versus exothermic reactions. And we'll talk about those later on in the chapter. But if you're touching a reaction vessel, like a flask or something, which I don't necessarily recommend, but sometimes it happens, you brush against something, you may observe that the flask is colder than your environment or warmer than your environment. That's a change in energy where you're producing heat or absorbing heat. We have to get together some kind of a shorthand language to be able to write these chemical equations. So we learned in chapter 6 about how to write names and formulas of compounds. Now we need to take that knowledge and apply it to writing chemical equations. Here what you see is some carbon being burned with oxygen. You need some heat, and you're forming carbon dioxide. If you like to grill, if you are a lover of barbecue or smoked foods, then you are familiar with this reaction. So there's some symbols that you need to know when you're writing chemical equations or when you're interpreting a chemical equation. To write a chemical equation, you're going to use an arrow to separate the reactants from the products. So what that looks like is you have your reactants on one side, then an arrow, then your products. Reactants are on the left, always. Products are on the right, always. Think of the reactants as your ingredients, and your products, that's the result. If you have multiple reactants or products, you separate them by a plus sign. So if A plus B come together and make D, you separate A and B, the two different reactants, with a plus sign. The delta sign, which is a little triangle, indicates that you use heat to start the reaction. So in that example where we had the carbon and the oxygen and it had the triangle over the yield sign, you gotta add heat. So if you're trying to grill something and you have some charcoal, you can't just put the charcoal in the grill and just put the food on it. You're going to look silly. You have to add some heat. The physical states of compounds are denoted in parentheses following each compound. So you need to let the reader know, is this a solid, liquid, gas, or aqueous? Aqueous just means dissolved in water. So all of that information needs to make it into the chemical equation. This chart summarizes the symbols that we use to write equations. Good thing to put in your notebook. It's an easy one to reproduce too, so if you don't have access to a printer, you can just kind of recreate it. Won't take you that long. But you'll need to know these. You will not get access to them on the exam. So make sure you know it. We're working towards balancing chemical equations. So you know the symbols and kind of where things are. Now we need to talk about what a balanced chemical equation is. All that means is that you've got the same number of atoms on the reactant side as you do the product side for each element. You're not gaining any atoms or losing any atoms. They're just being shuffled around. So in this image to the right, you've got 4 hydrogen atoms and 2 oxygen atoms. You have the same thing on both sides. So if we were looking at a reaction here, we could look at this and say, okay, there are 4 hydrogen atoms and 2 oxygen atoms. That's a 0. That's not a 0. That's an O. I know it's a little confusing. And on the product side, it's the same thing. 2 times 2 is 4 hydrogen atoms. And we've got 2 times 1 for our oxygen. That is a balanced equation. While we're gearing up for it, this is the goal. So keep that in mind. The goal for balancing an equation is to have the same number of atoms on the reactant side as you do the product side for each element. Right now, what we're going to do is a little bit of practice. We need to figure out the number of atoms of each element on the reactant side and the product side for this balanced equation. I'm going to show you the chart that I make, and this is the method that I use when I'm balancing equations too, not just checking for whether an equation is balanced or not. I put each element that I see, and I see P for phosphorus and Br for bromine. Across the top, I put an R for reactants and a P for products. That's my reactant side and my product side. I'm going to count up all of my atoms of each element on the reactant side and do the same on the product side. Remember, that subscript right there means that I have 4 phosphorus atoms. So that's what I'm going to write on my reactant side for phosphorus. For bromine, each bromine molecule has 2 bromine atoms. This 6 is a coefficient, aka a multiplier. So however many bromines I have in my molecule, I'm going to then multiply that by 6 because I have 6 bromine molecules. So 6 times the number of bromines in each molecule is 2. That gives me 12 bromine atoms. Now we go over to the product side. We've got a 4 in front, which is a coefficient. And then we've got a subscript of 3 for the bromine. That subscript is only for the bromine. So we've got 4 phosphorus atoms because we have to multiply everything in the compound by 4. It's just like with math. For bromine, I've got 4 times 3 because of that subscript. So I have a total of 12 bromine atoms. So this is balanced. It says that it should be balanced in the question. So if you got 2 different numbers, that would be wrong, okay? When we balance an equation, our last chart that we make like this, our check, should be balanced just like this is. So let's try balancing a chemical equation. This is the formation of aluminum sulfide. First thing you want to do is take stock of what you have. Take a lay of the land, if you will. Remember that the left-hand side is the reactant side. The right-hand side is the product side. Right-hand side is reactant side is pretty easy. we've got 1 and 1. Product side. Al has a subscript of 2. So that means there's 2 aluminum atoms. Sulfur has a subscript of 3. There are 3 sulfur atoms. Clearly not balanced, right? So this was our first chart just to take a lay of the land and see what we have. Now we've got to start balancing. What we do here is take the lowest common denominator. We'll start with the aluminum. The lowest common denominator between 1 and 2 is going to be 2. We don't need to touch the product side, but we need to multiply the reactant side. Wherever we see aluminum, we need to put a 2 in front. There we go. Now we do our second little chart, and this will show us what happened after we added that 2. Now you may be saying to yourself, come on, Dr. Hefner, do we really have to do a table for this? Well, probably not for this one. But when you have compounds that have multiple elements and you're putting a coefficient in front, you need to keep track of what's happening to each of those. Because you may have something that was balanced, then you put a coefficient in front, and now something comes out of balance. So the way you practice it is the way that you'll do it. I recommend doing this way if you want to be 100% sure that you catch every little detail. So we multiplied our aluminum by 2. Now we've got 2 on the reactant side and 2 on the product side. We haven't touched the sulfur, so we've still got 1 on the reactant side and 3 on the product side. We do the same trick with our lowest common denominator. We've got 1 and 3. Lowest common denominator is going to be 3. Multiply the reactant side by 3 to get there. Put a 3 in front of everywhere you see that sulfur, which should only be 1 compound. If you have the same element over 2 different compounds, it's a whole different ball game, much more difficult to balance. Not going to throw that at you. We do our final table just to check and make sure that we are actually balanced like our chart suggests we should be. On the reactant side, I have 2 aluminums and 3 sulfurs. On the product side, I have the same thing. So check and check. On your exam, you'll see questions about what are the coefficients in the balanced equation, or what is the coefficient for sulfur in the balanced equation. What that means is you're going to say what these numbers are in front. If you don't see a number, like with the aluminum sulfide, it means that you have 1, okay? We always assume 1. If I were going to write the coefficients in order, it would be 2, 3, 1. Those are the coefficients of the compounds in order of the balanced chemical equation. Notice that when we were doing the balancing, there's one thing that I never did. Never touched the subscripts. And that's because you shouldn't. So do not change subscripts. That would change the compound itself. That's not what we do. We add coefficients, which are the numbers in front. It may be tempting to change all the numbers. Don't. Only change the coefficient, which is the number in the very front of the compound. Here's another balancing question, and I'd recommend at this point that you pause and try it out. So I'll help you get to the point of having a chemical reaction, but this is a good example of what you may have to do for your homework or for an exam. You have a chemical equation that's written in words, and you have to write it out as a chemical equation with formulas. Balance the chemical equation when you've got this solid iron compound reacting with hydrogen gas to produce solid iron and water. So we have this solid reacts with hydrogen gas. That's hydrogen gas, okay? Hydrogen exists as a diatomic molecule, which we're going to talk about. But for now, just trust me. That's how you write hydrogen gas. Then we have our yield sign, and it produces solid iron and water. Water, remember, is a liquid, so you need to put that in parentheses. Now that we have our unbalanced equation, we need to take a lay of the land. See what we've got here. We have iron, oxygen, and hydrogen. On the reactant side, there are 3 irons, 4 oxygens, 2 hydrogens. Product side, 1 iron, 2 hydrogens, 1 oxygen. Clearly not balanced. So we need to just pick a place to start. Let's start with our oxygen. The oxygen starts off with the iron and ends up with the hydrogen. So if we make a change to the oxygen, it's going to affect both of those. Let's just get that done at the forefront, and then we'll figure out how everything shakes out. We've got a 4 and a 1. The lowest common denominator is 4. So where we see oxygen on the product side, we're going to put a coefficient of 4 out in front. Now that's going to change some things. Let's see what we changed. Reactant side, we didn't change anything. So we'll just copy that over. Product side, we should take our time. Iron, we didn't touch. Oxygen, we've got 4 times 1, which gives us 4 oxygen atoms. Hydrogen, we absolutely changed that too, because it's in the same compound as the oxygen on the product side. So that's 4 times 2 gives us 8 hydrogen atoms. Well, now we've got a little bit of a problem. We went from having our hydrogen balanced to now we've got 2 on the reactant side and 8 on the product side. We've got to fix that. The lowest common denominator with 2 and 8 is going to be 8. We multiply the reactant side by 4. So we put that coefficient out there. we do another chart. And I know it may seem a little bit tedious. But if you really want to make sure that you don't miss any details, you need to keep track of each change that you make versus just kind of throwing some numbers into the equation and just doing it in your head. If you have a record of what you changed and you can see, wait a minute, I'm not balanced. What did I do? You can undo the last thing that you did and start afresh. If you're just doing it in your head, you might kind of get lost and do some things that are unallowable, like changing a subscript. Okay, we don't want to do that. So we press on. We just did 4 times our hydrogen on the reactant side. So that gives us 8. Then we still have the 4 oxygens and the 3 irons. Product side, we didn't change anything. So we've got 1, 4, and 8. Last thing we need to do is balance that iron. The lowest common denominator between 3 and 1 is 3. So we're going to add a 3 in front of where we see iron. This should be our last table. Everything should be balanced at this point. If it's not, then we can go back, look at our math, but we've got a detailed analysis of what we did and where we may have messed up. So on the reactant side, we didn't change anything. So that's 3, 4, and 8 for iron, oxygen, and hydrogen. Product side, we multiply the iron by 3. So that gives us 3. And then everything else remained the same. Now we're balanced. The coefficients for this would be 1, 4, 3, and 4. So keep that in mind. We don't have a coefficient in front of this solid iron compound. But if you were doing a homework question or a quiz or anything like that, the coefficient is 1. Now we need to make it a little bit more complicated because it wouldn't be chemistry without it, right? Remember those polyatomic ions? The compounds that you had to learn how to name and write formulas for? You can see those in chemical equations. The good news is, if you observe a polyatomic ion on both sides of your equation, you can treat it as one unit. PO4 is phosphate, and we see it intact on both sides of the equation. When we make our charts and we do our balancing, we can actually keep that PO4 all together just like we do with the elements. We treat it as one unit. First table, we take a lay of the land. We've got sodium, phosphate, magnesium, and chlorine. Let's count them up. 3 sodiums, 1 phosphate, 1 magnesium, 2 chlorines. Remember to look at those subscripts, and for the PO4, we're considering the whole thing as a unit. We're counting that as 1. Product side, we've got 3 magnesiums, 2 phosphates, still, 1 sodium, 1 chlorine. Whoa Nelly, very much not balanced. What do we start with? Start with balancing the polyatomic ion. The lowest common denominator between 1 and 2 is going to be 2. We put a 2 in front of the compound that contains phosphate. Now we check and see what we made a mess of. Because it gets a little bit messy before it gets better. It's kind of like life. Nothing wrong with a little bit of mess. So we put a 2 in front of that sodium phosphate compound. That means that instead of just 3 sodium atoms, we've got 2 times 3 because we've got 2 of these now. So there's 6 sodiums. We have 2 phosphates. And we didn't do anything to the magnesium chloride, so those numbers just stay the same. We also didn't do anything to the product side, so those numbers are still the same. Next thing to tackle. Let's finish balancing the sodiums. We did the phosphates, we started messing with the sodium. Let's mess with the sodium some more and get that squared away. Lowest common denominator is going to be 6 between 1 and 6. So we're putting a 6 in front of the compound that has sodium. Let's see what we did. Sodiums and everything on the reactant side, we didn't do anything. So we should be able to just copy it. The product side, however, we made some changes. Let's see what we messed up. So, magnesium, still the same. We've got 3 of those. Phosphate, still the same. 2 of those. Sodium, we now have 6. We also now have 6 chlorine atoms. So the last 2 things that need to be balanced are the magnesium and the chlorine. And thankfully, on the reactant side, they're in the same compound. So whatever we do to one, it's going to happen to the other. And that better make them match up. We'll do the chlorine since that's a little bit messier. And we'll make sure that that lines up with the magnesium. We've got 2 and 6. Lowest common denominator is going to be 6. We're going to put a 3 in front of that magnesium chloride. And that makes sense because if we looked at the lowest common denominator for the magnesium between the reactant and the product side, it would be 3. So, putting a 3 in front of that should make us right as rain. But we need to double check and make sure that we really are done. I just said right as rain. I don't even know where that turn of phrase comes from. Why is rain right? Let's see what we did. Sodiums, we didn't touch them, so it's still 6. Phosphate, Didn't touch them, should still be 2. The magnesium and the chlorine we did touch. It's 3 times 1, which gives us 3 for magnesium, and 3 times 2, which gives us 6 for the chlorine. The other side should be the same, but always double check and make sure. We've got 3 magnesiums, 2 phosphates, 6 sodiums, and 6 chlorines. Everything matches up, so we're good to go. That means our coefficients, in order from left to right, are 2, 3, 1, and 6. I should mention here, before we move on to the next section, that all of these coefficients, they're small whole numbers. And we should also have the simplest ratios. So if I doubled this to say 4, 6, 2, and 12, yeah, that's balanced, but it's not the lowest or the smallest coefficients that you can have. So make sure that your coefficients are whole numbers and that they're as small as they can be. Can't reduce them any further. Moving on. We did balancing equations. We're pros at that now. Let's talk about types of chemical reactions. These are the types of chemical reactions that you will be responsible for. We're going to go through each one in detail, so I'm not going to list them off here. We're just going to go through one by one. First one we'll attack, combination reactions. In a combination reaction, you've got 2 or more elements forming one product. You're taking simple ingredients, putting them together to form one complex thing. Your example here is taking sulfur and oxygen gas, and you're creating sulfur dioxide. 2 simple compounds combining to form one more complex product. You've got some other examples here where you're taking another metal plus oxygen and making an oxide. You've got sodium and chlorine, so a metal and a nonmetal. Many types of examples. All of these are combination reactions. You're combining things together, plopping out one product. It's kind of like if you're making cookies or brownies or anything like that, where you're kind of mixing it all up in a bowl. Oversimplifying how you make good cookies, by the way. So don't just plop everything in a bowl. But you're taking all these ingredients to form one thing, a cookie. In a decomposition reaction, you've got one reactant that is split into more simpler substances. So 2 or more simpler substances. I'm struggling with the word substances today. You have something that's complex, like in this example, you've got mercury 2 oxide. And it decomposes to make liquid mercury and oxygen gas. So you've got one complex thing, 2 or more simpler things. You can think about the decomposition reaction as the reverse of the combination. So if you can remember one, just know the other is the opposite. Next type is a single replacement reaction. In these kinds of reactions, one element takes the place of a different element in another reacting compound. So let's say that you've got A, and you're placing it into a solution of BC. Okay? So A is a solid of some kind, BC is an aqueous solution. A kicks B out and says, look, you didn't pay your rent. You've been a bad roommate. I've been called in because C is needing some help, okay? C has been footing the bill for the rent for the past 4 months. You need to get out, B. I've already got my rent and security deposit, so bye. It becomes part of that aqueous solution. And B is like, well, dang, I'm out here reckless. Lost it again. With chemicals, some examples would be zinc solid added to hydrochloric acid. The zinc is active enough to replace the hydrogen in the acid. You end up forming zinc chloride and you liberate hydrogen gas. This can also happen between two metals. If you have copper 2 sulfate solution, which is a nice pretty blue color, and you add some source of solid iron, what you'll see is the copper in the copper 2 sulfate will actually start to come out of solution and kind of form it'll plate onto that iron. So you'll coat the source of iron, and the iron will become part of the aqueous solution, and you'll have iron 2 sulfate. In a double replacement reaction, you've got the positive ions in the reacting compound switching places. So A and B are roommates in their own little aqueous apartment known as a flask. C and D, they've got their own place across the hall. Then they swap roommates. A and D become friends. Maybe that's still aqueous, but C and B, you might make a precipitate, some kind of a solid, or you might liberate a gas. But you make two different compounds because you took two aqueous solutions, mixed them up, and you made something different. You could also have a solid, but as long as you've got two different ions in each compound, then you can have a double replacement reaction. Now, some real world examples would be silver nitrate and sodium chloride. You mix those two, you make silver chloride, which is insoluble, so you form a solid, and then you have sodium nitrate, which is aqueous. So a new aqueous solution and a solid forms, called a precipitate. You could have zinc sulfide, which is a solid, and add that to hydrochloric acid. You're going to make aqueous zinc chloride and liberate hydrogen sulfide. Combustion reactions. This is a reaction type that you're likely familiar with, even if you don't know it. If you drive a car or have ever ridden in a car, a bus, a motorcycle, anything like that, combustion reaction is what gets you going. You're taking your fuel source, which is gasoline or diesel, combining it with oxygen, and that burns. You form carbon dioxide and water. You also release a lot of energy, and that energy is what's used to propel your vehicle forward. To define a combustion reaction, you have to take something that's a carbon-containing compound. So gasoline and diesel are examples of carbon-containing compounds. You could also have CH4, which is methane. You could have propane. Any of those are carbon-containing compounds. You burn it in the presence of oxygen, and you form carbon dioxide and water. This table, table 7.3, gives you examples of each of the reaction types we just covered. Great to reference when you're doing your homework. If you enjoy having this kind of a reference in your notebook, go for the gold. Otherwise, the notes that you have, whether you just print out this presentation or you write it down in your notebook, should be sufficient. So I would recommend, if you haven't while taking notes, go back and write an example for each of them so that you have something to compare your homework and quiz and whatever problems to. Time for a learning check. We've talked about all these reaction types. Let's actually try to identify each reaction. I recommend pausing it here and trying to label each of these A through E. Then rejoin me and see how you did. So in part A, we are taking two simple reactants forming one complex product. We're combining things to make one product, which means it's a combination reaction. I abbreviate reaction RXN. Second one, we've got silver and some kind of an aqueous solution. And I notice, look at where that silver ends up. It has swapped partners. It was alone, then it booted out the hydrogen. So that must mean it's a single replacement. Part C, we've got a carbon-containing reactant here, plus oxygen. We're making carbon dioxide and water, and a lot of energy. Has to be combustion. Part D. Once you start seeing all of those polyatomic ions and stuff, it looks like ionic compounds, be on the lookout for replacements. I like to use colors to demonstrate whether or not something has switched partners. So if I give each element or ion its own color, then I can see what happens much more easily. And it absolutely looks like we have a double replacement. The lead is now with the sulfate. The potassium is now with the chlorine. Final reaction, letter E. We've got something that's complex, and we've got two simple products. This looks like the reverse of letter A, so it must be decomposition. Get comfortable with that kind of logic. That's what you need to identify reactions. And don't be afraid to use the color pencils, or markers, or highlighters. All those things are allowed on exams, so go crazy. Still in the realm of talking about reactions. Now we're going to talk about one specific reaction type, which is oxidation-reduction reactions. I will very likely abbreviate that redox. Same thing. An example of a redox reaction is rust forming. What happens with redox reactions? Well, redox reactions are great because they provide us with energy from food. So not all, but a lot of the chemistry that happens in your body has to do with redox reactions. It's also the reason why your phone, your laptop, and all the things that you have that have a lithium ion battery in them can produce electrical energy. And like I said before, it's also why things with iron rust. That is a redox reaction. What happens in redox reactions is that you're transferring electrons from one substance to another. If A has an electron and it transfers that electron over to B, then that means that B is going to receive an electron and be reduced. Reduction is the gain of electrons. A, however, just gave up its electron. It lost it. Oxidation is the loss of electrons. So one way that you can remember oxidation versus reduction is using this mnemonic here, oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Oil rig. Now, when I was coming up through chemistry, like general chemistry and stuff like that, we learned Leo the lion says grr. Lose electrons, oxidize, gain electrons, reduce. Whichever one helps you, or if there's another one out there on the interwebs, use it. If you can just straight up remember the difference, that's great too. But I think that these little mnemonics are silly, and they kind of help make chemistry a little bit more light and fun. I have young children, so we make animal sounds all the time, and going grrr every once in a while. It's got to be healthy, right? Kids are happy, so why not try it? Back to redox. Statue of Liberty, if you've ever seen it, it's green. Didn't start off that way. It's actually green because the copper metal in it oxidized. What does that mean? Copper metal, which you see this 0 up here, that's just a charge. A charge of 0 means it's neutral. When you get into electrochemistry, it is very commonplace to see a 0 for a neutral substance just because it's easier to track when something gains or loses electrons. So we've got two half reactions here. What happens to the copper and what happens to the oxygen? Copper starts off, it's neutral. It's got no charge. Protons equals to electrons, okay, in terms of the number of them. But the copper is oxidized, which means it loses electrons. Notice how now it's a positive ion. And we have lost 4 electrons. With the oxygen, O2 gas, neutral. It's going to lap up those 4 electrons because oxygen is very electronegative. Since we have the electrons on the reactant side and we're adding to the oxygen, that means that it's going to gain electrons. So if you're losing electrons, you'll see something positive being formed, and you'll also see some electrons on the product side. If you are gaining electrons, then you'll see those electrons on the reactant side. This is another example of a redox reaction. It's a single replacement reaction. You've got zinc being oxidized to zinc 2+. If you have a solution of copper 2 sulfate, which is a very pretty blue, and you add a zinc strip, wait a little bit, and what you'll see is the copper will start to plate onto that zinc strip, and you will have released some zinc ions into solution. So that's an example of a real-world reaction that you could do if you had all of these components at your disposal. Like I alluded to, redox reactions are really important in biological systems. One example of a molecule that does redox in your body is a coenzyme called FAD. Coenzyme just means that it's a helper to an enzyme. The enzyme needs this molecule to do the chemistry that it does. Now, I'm a biochemist, so this kind of thing is exciting to me. I talk about it forever. It's great, but I won't do that. FAD, which stands for flavin adenine dinucleotide, can be reduced to form FADH2 by the transfer of 2 hydrogen atoms. And we're talking about the proton and the electron. Okay, so we're transferring a couple of electrons to FAD and reducing it. That can be reversed too. FADH2 can give up 2 hydrogens and be oxidized. So this is a very handy biological molecule that can do some really interesting chemistry. Lots of enzymes in the body use it. Very, very important. This table summarizes the characteristics of oxidation and reduction. Oxidation always means that you're losing electrons. Ways that you can see this is the addition of an oxygen or the loss of a hydrogen. So those are some examples. Reduction always means a gain of electrons. It may involve the loss of an oxygen or the gain of hydrogens. This is another summary slide which gives you more information about oxidation and reduction. If you're a chart person, you got your chart. If you're a word person, you got all the words. So it's the same thing as the chart. There are more biochemical redox reactions that we could talk about. If you're metabolizing alcohol, so methyl alcohol is poisonous. Don't test that. It is poisonous. Your body can metabolize a little bit of it, but it is poisonous. One of the reasons it's poisonous is because you're forming intermediates that are poisonous. They're toxic to your body. So you're making formaldehyde and formic acid before you finally make carbon dioxide and water. Formaldehyde and formic acid are toxic to you. They'll cause headaches. They interfere with reactions. Bad, bad news. So please don't try it. But the body is amazing. And it can sometimes take the things that we do to it, the bad things that we do to it, and figure out how to solve it. That is beautiful chemistry right there. Let's do a learning check. You need to identify when something is being oxidized and when something's being reduced. So this should help you with that. Take a second and try it on your own, and then join me and we'll talk it through. We need to figure out which reactant is oxidized and which one is reduced. Let's look at what happens to the silver. We're starting with Ag+. And we're going to Ag, which you can kind of write in a 0 here. If you don't see any kind of a charge, that means 0. So we're going from positive to 0. The only way that we can do that is if we add an electron to get rid of that charge. If we're adding an electron to the silver, that means it's gaining an electron. If Leo, the lion, says grr, then gaining electrons means reduced. So Ag+ is reduced. The chlorine, we're starting with Cl- and going to Cl2, which again doesn't have a charge. There's a 0 there. You just don't always see it. You can write it in if that helps you. To go from a negative charge, and we'll have 2 of these, to a 0 charge, it means that we must have gotten rid of some electrons along the way. We lost electrons. Remember, losing it means that it's on the product side. So that means the chloride ion is being oxidized. If this was confusing to you, then you should revisit what it means to gain electrons and lose electrons. And the first place that we started talking about that was in Chapter 4. So revisit Chapter 4, make sure that you're comfortable with gaining electrons and losing electrons and what that does in terms of making ions. We also talked about that in Chapter 6 when we were writing formulas and writing names. So those are 2 places you can look for more information about forming ions and what that means. That's it for the first part of Chapter 7. Please make sure that you watch the next 2 videos. I know, it's a lot of material. 2 videos and we already an hour deep. But I promise you want all this information because Chapter 7 is really big. Make sure you come to live lecture. We always do practice problems. You get all the details regarding assignments and exams. So come join. Until then, be safe.